and share my screen. See how it goes. We're all here. So I'm still gonna record. Okay, welcome back. Still grading presentations. My rubric was a little more rigorous than I thought, so I have to go through it again. But it'll be done by Thursday. So I'll have that done. But so today I'm going to give a talk on electrical properties of conducting nanocomposites, specifically tolerant-based nanocomposites. And so I want to start with some basics before we get on too far. First of all, you know, electric current is an ordered movement. Oh, display on. I get one adapter and everything falls through. So electrical current is an ordered movement of electric charges. So you have to have a potential that allows it to go from one place to another. These charges are called current carriers, okay? Not everything that carries current carries it with electrons, okay? So you can actually have ions move, you can have other things move in the system, but what we're gonna be talking about in this is electrically conductive. And in metals and semiconductors, electrons are the charge carriers. Okay, so that's the ones that are going to carry stuff. And so before we can talk about, you know, that, I want to talk a little bit about band gap theory and what that means as far as how easy or hard it is to get things to be conductive. So in the case of band gap theory, we're thinking about in every atom, they fill the electron shells from the bottom up, right? And at some point, you're going to have where the shells are going to start getting closer and closer together. And so there's going to be a very little barrier between them. Now, that's for an individual atom. Now hook them all together as a molecule or as a metal surface. And now what you have is the bands are very close together because they're all kind of mixed together. And if those bands are really close together, or if the highest occupied orbital, oops, wrong tool. If the highest occupied orbital is right next to the lowest unoccupied orbital, it's easy to excite an electron into that band. And when it gets excited into that band, and that band, when it gets excited above the Fermi level, which is where electrons can then be conductive, it can then move freely. So that's why when we look at metals, we see that the metals have both empty and free bands right at the Fermi level, okay? So it's very easy to get electrons to flow in metals. Now in semi-metals, it's not as easy. They don't have as high a conductivity, and that's because they have fewer orbitals at the Fermi level, even though they have orbitals there that are unoccupied, that can have electrons excited up into them, it's not as easy. But then we get into this next set here, which is what we call the semiconductor band, okay? And in an intrinsic semiconductor with no doping of either type, the Fermi level is typically in the middle between the highest occupied, which are the ones down below, and the unoccupied ones. Remember, those electrons have to be excited into those other orbitals to be able to freely move. Okay, so in a case of a p-type, we have the Fermi levels very close to the lowest occupied level. I mean, the highest occupied level. And in the case of n-type, the Fermi level is closer to the lowest unoccupied level. And so what we'll see here is that different things move in different places. And then, of course, when the gap's too big, we can excite electrons into that upper level. It's an insulator. Okay. So in metals, we actually turned out that, you know, those are so close in energy that they can freely dissociate the electrons into the surface as it goes around. And it's going through what they call a lattice, or a positive ionic lattice, okay? So imagine it's literally along the surface, this sea of electrons that can move. The sea of electrons that can move are what conducts the electricity in metals. But here, the difference in the potential from one point to another point, it tells you which direction the electrons are going to drift back and forth. But they don't drift that fast. It's not instantaneous. An electron put in this side of the wire does not shoot out at the speed of light somewhere else, because this electron is actually going to be moved forward, drifting toward that potential. And then it's going to push another one by electron-electron repulsion, and it's going to push another one, another one, another one. So it's a cascading effect of this one moves, brrr, boom, brrr, and the effect is it looks like it's going at really fast speeds, because what you're doing is you're just using electric repulsion to get the electrons going through the wire. So it actually, the drift of an individual electron is actually kind of slow, like meters per hour. But you have so many electrons you're shoving in this side that you have to fall out the other side due to electron-electron repulsion. So that's where we get the conduction in metals from. Okay, so in the case of semiconductors, we have to have that Fermi band has to be at a reasonable level so that we can excite electrons above that Fermi band so they can be dissociated and move around. And this applies to intrinsic undoped semiconductors. In intrinsic undoped semiconductors, as you cool things down, the energy required to get into that upper level is no longer available. So what it means is that at absolute zero, intrinsic semiconductors actually have infinite resistance and zero conduction. Okay, so likewise, if you have a semiconductor and you heat it to a higher level, it will have higher and higher conduction.
Would a metal at zero still have conduction?
Yes. Yeah, because they're at the level, right? And then superconductors are a whole different ballgame. So in doped semiconductors, the dopant ions increase the charge carrier concentration. And when you increase charge carrier concentration, you can increase flow and current. Okay. And notice that most of these are going up into the, you're exciting electrons from the band, the lower band, the filled band, into the upper band. When you excite electrons into the upper band, you're leaving holes behind in that valence band, the lower, what used to be the occupied band. And these holes are, just are able to, you can think of them as, those are deficits of electrons that also have flow, and they flow in the opposite direction of the field. Okay, both types, the donors and acceptor molecules, when you increase the dopant level, you will decrease resistance. Decreasing resistance increases your conductivity.
This is probably a little bit out of the scope, so I'm sorry, but when are the holes moving? Is that considered current, or would that?
Technically, the electrons pushing the other electrons out of the way. So this electron is moving this direction because of the field, right? Okay, but it can't move without pushing another electron. So that cascade of pushing those electrons, that's the flow, that's the current.
So, go ahead.
That's the valence band you're talking about pushing.
No, when you have the semiconductors or even the metals right here, it's the occupied electron, the occupied orbitals right above the Fermi. So the ones that are actually the electrons that are moving in the now doped band, and the holes are moving in the where the electrons used to be.
I guess I'm saying, is a hole a physical, measurable thing, or is it just a lack of an electron? It's just something I've never really understood.
It's an unfilled orbital, so it's an actual thing. You've taken an electron out of where its energy state should be and raised it into the conduction band. Therefore, it's an actual thing. Okay. So in composites, it's a little bit different. Because in composites, you have a dielectric material, a material that resists flow of electrons, and you're filling it with something that promotes the flow of electrons. So you have this combination between the conductivity of the component and the resistivity or dielectric constant of the material. And what happens is until you get to a certain level, there is no path for electrons to flow through your system. And you have a very low conductivity or a very high resistance. At some point, and it's called the percolation threshold, there are at least one path where electrons can move all the way through the dielectric material to get out to the other side at where the potential is. So what we're looking for in our composites here is we're going to see a lot of things where loading levels are increased till we find what the percolation threshold is, and where the percolation threshold changes based on processing, aspect ratio of your material, and conductivity of your material, of your conducting filler. The CF is conducting filler. Okay. Now, that means that we have an order effect as well. If you have randomly distributed particles, you're not going to, it'll have to have some random walk path of the electrons flowing through the system. Okay. But in the case of if you have like all of your nanofibers kind of aligned, the end-to-end distance between them is going to start to get a lot closer together at that lower filler concentration. Okay. And so when we measure that percolation threshold, we're actually measuring different concentrations of filler or different processes, and then looking for that change, rapid change in conductivity. So there's,
If they're aligned, can't electricity only go one way? Or can?
no, because we have, it depends on if you only have one string of conductive things, they'll go back and forth.
Sorry, I meant if we're aligned in the x-axis, we can only have current go on the x-axis.
Not necessarily. If your long aspect ratio things are close enough together to be able to hop back and forth between the other fibers, then you can get, there might be a difference in the conductivity across the grain and with the grain. And I'll show you some examples of that. But just, you know, it doesn't mean that the entire, it's completely resistive in the off axis. It's not completely resistive. And the reason is we have hopping and we have tunneling of those electrons. So as these electrons are moving through your dielectric material, there's two ways they can move. They can move by hopping, which I'm going to zip up this conductive material. I get to the end and I need to find the next place to conduct. I still have a field drawing me to this side of the system, and then I can hop to the next system if I have enough energy to make that barrier. And that barrier is usually somewhere around 20 to 25 angstroms. Okay, I can hop to the next one and then zip up that conductive thing and then hop to the next one, always being drawn toward the positive side of the field. Okay, so the difference between tunneling and hopping is that you can actually get these electrons to go jump through the barrier of the dielectric even without enough energy, and that's field-based. And so we can actually have a combination of both hopping and tunneling. So you have all of your different fillers, and let's say you get to the end of this long aspect ratio here, and there's nothing right in front of you to hop. So you're going to hop to the closest thing in any direction, three-dimensional direction. So you can hop laterally and zip up that one and maybe hop laterally again. So your conduction doesn't go 100% only in one direction, even in an ordered system.
Is the energy, the barrier, is that dependent on the conductivity of the matrix?
It depends on the dielectric constant of the insulative material, and the field. It's field, dielectric constant, and distance. Okay, so I know this is review, but I gotta just make sure everybody's on the same page here. So when we're looking at these papers, we're looking at different units of measurement. Resistivity or resistance is measured in ohms, and that's one way to look at it. And a watt is a unit of power, so it's actually current over voltage, or current over voltage over current. Anyway, it's current is actual flow, and potential is the energy difference between the two things. And yeah, okay, there we go. Voltage, yeah, is the potential difference in electricity between the 2 points. and is measured in volts. You can think of it as electric pressure. So it's like pulling vacuum, right? So you have at a high vacuum, you have more molecules than in a low vacuum. But in this case, if it's a high field, you're going to have more carriers, charge carriers coming through the system if possible. But then you also have current, which is measured in amperes. And that's really the number of electrons being cascaded through the system. And then the dielectric constant is also called the relative permeability, permittivity. That means permittivity is basically how easy can electrons flow through your system. And it's measured as a ratio of vacuum. So how do electrons flow in vacuum? Compare that to your material. Most polymers are dielectric with a factor of 2 or above. And so, but most metals are right at 1, the same as vacuum. So we'll see that come up a time again. Okay, so let's define resistance. Resistance is measured by looking at the length of the sample, the cross-sectional area of the sample, and the electrical resistivity or specific electrical resistance. And that's per the material. The specific resistance actually does not depend on the sample size or shape, which is why the units are in ohm meters. But once you have the ohm meters plus the cross-sectional square meters and then the length, we're going to end up with our resistance. All of the meters cancel out and you're left with ohms only. Okay, so that's resistance. In contrast, conductance, which is usually with the big letter G, is measured about the same way, but what we're looking for is that length to cross-sectional area, and then we're looking for sigma. Sigma is the electrical conductivity, and that's measured in Siemens per meter. And again, when we look at this, we have the Siemens per meter times area divided by the length. All of the units cancel out, and we end up with Siemens as our conductance. Okay, so what do we care? Would we care for measuring conductance or resistance? Well, you just measure one or the other depending on which part of the conductivity scale you are in. But it turns out they're proportional constant and not dependent upon geometry, and that makes them reciprocals. So 1 over conductivity is resistivity, 1 over resistivity is conductivity. So there's a really wide range of conductivities available on here. I think it's one of the widest ranges that we can actually measure. The highest conductor that's not a superconductor is here 10 to the 6th silver. It's interesting, silver, copper, and gold are all in the same row in the elemental, and they all have here the 3 highest conductivity. Not sure why, but they're almost filling that. And then once we get to our semi-metals, this is our first semi-metal business. And notice there are fewer bands. There's fewer bands in that Fermi level, and so our conductivity starts to drop. And then we have our classical semiconductors, germanium, silicon, and cadmium sulfide. Those range depending on how they're processed, what their impurities are, and what their dopates are. So you can get anywhere in that range. But notice that pure glass, silicon oxide, is down here, and if it's perfectly ordered, quartz, one of our lowest conductivity. Fused quartz is one of our lowest conductivity. And diamond's pretty low too, but it has a very high thermal conductivity. It's low because it has only carbon atoms and very high valence. So when we look at this, we think about things that we want to use as a conductor to transfer or sense things. Semiconductor, where we want to switch things based on thermal or other things. We can change the conductivity by raising the temperature as well. And then our insulators, do we want to insulate? So it's by use on what we want to use in our system. So for example, if we wanted something that transferred a lot of heat but no electricity, we'd want to fill it with diamond or quartz. hexagonal barium boron nitride to get that system. Okay. So any questions yet? Oh, you've been asking questions. So that's fine. Okay, so let's talk about some of the standard measurements that people are going to be doing when doing these nanocomposites. They do different measurements based on what kind of testing they're doing. So if you're just looking for conductivity and or threshold, we're going to look at surface resistivity measured in ohms per square, volume resistivity measured in ohms per centimeter, surface resistivity if you're looking at ESD, which is electrostatic dissipation. And then you can also do electrostatic dissipation as a static decay, which is actually just a time it takes the field to go away. And then we also have, if you want to attenuate radio waves, you want to do EMI shielding, electromagnetic interference shielding. We're going to do that by a different method, and that's usually going to be decibels of attenuation. So how much quieter is your output? Okay, so let's talk about surface resistivity. The classical one is used in this little square thing right here, where they're held exactly the same distance apart on all measurements here, and you measure the resistivity across the surface of the material. Usually you glue on or you silkscreen on a pattern and then you measure it. A lot of the commercial ones look more like this with this round electrode, and so we have two electrodes that you silkscreen onto your sample. The inner electrode is, I believe, the ground. The outer electrode is actually where you apply the field. And you measure the resistivity, or the resistance to flow of electrons between those. And when we do that, we're not going through the bulk of the material. There's actually only a certain penetration of threshold, so that's why it's a different measurement than the other one. And so, because of the tradition of having it in this square electrode, the measurement is in ohms per square. And so we can see that happening. And these machines are readily available for $5,000 to $10,000. A lot of the times when you do the surface resistivity, you'll actually put a weight on it, a constant weight, to make sure you get good surface contact. I've done this where the silk screen pattern is actually about this big. I've done it where I've silk screened on silver paste and then use that as the contact for the surface resistivity. In contrast, the volume resistivity, you put one on top, one on the bottom, but you still do it with a weight on it such that you can measure so it'll have good contact in between the system. Sometimes they'll even pull vacuum on the system, but most of the time not. So what you're doing is you're actually measuring through the thing, and so we have the area of the electrode and the thickness you're going to. Okay. This is probably a better test than surface resistivity when you're doing nanocomposites, because you're looking for the homogeneity through your entire system, not just what happened to end up at the surface. Okay. Now, if you're looking for stuff like dissipation, static dissipation, you might only want it at the surface, so let's do your product. So you have to choose your test based on what your application is. But this is one of the ones that we'll see a lot here, because this tells you a lot about the bulk electrical properties of your system, not just the surface electrical. But one thing I should mention is the surface electrical properties actually change with humidity. So you can absorb something to it, you can absorb something, and that will change your surface resistivity. And that's another reason why the bulk or volume resistivity is actually a more constant number, because you're never going to get the entire volume of it blended with whatever is contaminating your system.
That constant volume resistance is dependent on the material that we are testing.
The resistance is dependent on the what?
The volume resistance is a parameter, is a constant that dependent on the material that we use, that we are testing.
So
How we obtain it actually.
oh, well, there's, for this one right here, this is the top electrode, the weight is the bottom electrode. And if it can measure down to like 10 to the minus 18 Siemens. So what you'll be able to do is, if you can't measure it, you just get a thinner sample. And you can get, in fact, a great one to do would be to make 3 thicknesses of sample and see if it's one that. See if it gives you the same 3 numbers when you count the thickness.
They probably don't use the
Did that answer your question?
So yeah, we have to measure that the body resistance too before measuring the resistance.
Well, measuring volume resistance counts as measuring your resistance, because think about the way the way this is set up. You have one electrode. The cross-sectional area is the area of the electrode. The length is the thickness of your sample. So you're measuring it the exact same way, except usually when we're doing it, we're not doing a meter of material, so we only do a centimeter or less of material. So that's why it's usually in centimeters.
But the area is only the electrode.
The electrode area. The electrode area, and they should now.
The weight, they probably can't do that for like flexible materials, right? Won't that affect the
The weight can be used on, unless they're really soft, like silicones right there. Most things do not deflect under, I think it's a 1 or 2 pound weight is the standard use. There's a standard weight that comes with the whole kit and everything. And it's usually not enough to deflect a standard material. And that's actually an interesting problem, because let's say you have a really soft silicone and you don't put a weight on it, and then you have X conductivity, you do put weight on it, and it now has a greater conductivity. Because now you've squeezed all those pathways closer together because of the compliance of the material. So, but they probably have a special thing for silicones, but I know it's a standard weight for all plastics. So then if you want to actually just do ESD or static dissipation, you actually have a different one. It's closer to the surface resistivity, but it's a smaller cell. And it'll measure it for these planar materials. And it also, I believe, has its own weight loaded in it as well. So it's basically the same thing. It has a ring and a disc, and you put a field across that and measure the conductivity. And that'll give you a surface resistance in ohms. ESD. Okay. Now, another way to do that is you can actually look at what's called static decay. Now, this is coming under fire under ASTM because of the even though everybody kind of does it the same, everybody gets different numbers. So they're kind of like, this is kind of losing some of its testing ability. They're going to switch over more to the surface resistivity for the ESD, this one right here. But the idea here is that you would just put your electrodes on your material. You apply a field, usually something like 2,000 or 3,000 volts, and then you disconnect the field, and you see how long it takes for it to drift back down to 0. So things that have almost no conduction keep that charge on that surface. So you can think of anything that you've rubbed that has static electricity built up on it, that field will stay there for hours. You know, in this case, well, maybe not hours, but definitely long seconds here. So Lexan and Teflon can't dissipate that charge anywhere, not even into the air very readily. However, once you start getting things that are hydrophilic or something that's coated, you're able to dissipate that charge much more rapidly.
That's because why would that?
Hmm?
Why is that? Why?
Well, the water on the surface,
The water is not.
no, but it helps dissipate the charge. So, but you know, it's material dependent as well. I mean, if there's any, you know, the higher the resistance, the more likely your surface charge. But there has to be some other purity or pathway. Most of the things that are coated is just like nanometers of aluminum, and that's enough to dissipate the charge. It's not a lot of current; it's just a lot of potential.
Which material do we do best? Like, we want to get it dissipated very fast, or we want to dissipate it gradually?
Depends. Most of the time, we want to dissipate it fast. For ESD, you don't want static to build up on any of your work surfaces, or else it'll arc where you don't want it to. So most of the time, you want it to dissipate very quickly. Less than a second. So the EMI shielding is a little bit different. In the EMI shielding, what we do is we get a radio frequency horn, and a radio frequency analyzer over here to get over here. And then these horns are tuned to the frequency that you have, and you put your sample right in the. Okay, and then you measure the radio frequency as a function of frequency. You measure the sound coming out of it with nothing in the chamber. And then you measure it with the thing in the chamber. So you'll see this goes from not quite to gigahertz, but it goes a really long way. You usually measure this from like 1 hertz to, well, they're going all the way up to like 50 gigahertz now because of some of the 5G and 6G and 7G. They're planning new frequencies that they can use. And so they're starting to test way up into the gigahertz area. And sometimes you can actually have that in vacuum, and sometimes you can have that in air, depending on which one you want. But the sample's just held in here. So the idea here is that every 3 decibels you go down in energy, every 3 decibels you go down, it starts absorbing. I can't remember the exact number, but it's something like at 21 decibels, that's 99.99% shielding or something like that. So this is a lot of shielding. And notice it's slightly frequency dependent based on the materials. Okay, so this would be a lot for if you were going to make materials that were coating wires for communications or stuff like that. All right, questions on those tests? Okay, so I'm going to start with graphene-based systems. Got a great review article on this. Recent progress in graphene polymer nanocomposites from Advanced Materials. Literally, it came out, last year. And this is a look at the number of publications coming out for polymer-based graphene nanocomposites, inorganic, non-metallic, which would be like ceramic nanocomposites, and then metallic nanocomposites as well. A lot of that is the organic metal framework structure stuff too. So, it's got some organic in it, but it does have quite a large variety of uses. So graphene is really probably almost as well studied as carbon nanotubes now. Okay, so one of the things I brought out of this article is the effect of order. And in the case of these, we're looking at the electrical conductivity by graphene content. And we're seeing if order affects things. And so the ones in the blue square, the black squares in the blue boxes here, these are different articles that have different conductivities based on their loading. And these were just done randomly. They were just like stirred or a solution processed or something like that. But if you kind of pre-network or get your material to be like have a structure before you add polymer to it, if your graphene has structure before you add polymer to it, then you have a higher conductivity there. And then in this one right here, we actually see this aligned pre-network parallel to the direction of alignment and aligned vertical direction or orthogonal to the direction. And they're still higher. So order is everything. Why? Because of the percolation. So you're going to have more things that are closer together. It'll have the ends closer together, and you'll have more pathways, more conductivity. So that's why its order really has a great effect in graphene. And remember, graphene is technically a 1D, right? And everybody draws it as this perfect flat sheet. Well, no, they wrinkle and fold and everything like that. So you can have them kind of all bent around, but now if you order them and try to lengthen them like that, you now have 2 different axes that run very long distances. And it's just our nano axis that has a small size. Okay, so let's look at a percolation via aligned network. In random systems, we're looking at our percolation threshold usually in the 20 to 30%, which is exceedingly high. But the idea that they're not perfectly flat anymore, they're being kind of twisted around together. And we'll see that as they finally get to the jumping, the hopping distance here, we can get to some decent conductivity. Now, if you have this pre-ordered, pre-aligned, so that you have some of your order before you add your polymer, then line goes away, the line goes down, and our percolation threshold starts at a much lower thing. And that's because you've already set up half of your connections before you do the other. Now, if you pre-order but then align, we're going to see a much higher, much lower content needed because we're not only pre-ordered in a certain fashion, but then we're aligned and get to even a lower concentration to get to that percolation threshold.
I'll read the paper, but do you remember like how they were able to achieve that pre-network?
I didn't actually, I'm not going to present the pre-network, but I was going to present the aligns network. So, but here is I did actually look at the pre-network, and it was directional freeze drying or freeze drying. They kind of made a graphene oxide aerogel, and then they reduced it, then they processed it. But I'm gonna actually show you how they did the aligned, pre-aligned. Okay, so this is some of the results they showed. It's from, random, we're looking at like 30 to 58% to get the conductivity in about the same range here. And it gives the EMI shielding of about 30, which is kind of what's, I think somewhere around 30 is what people are looking for just basic electronics. So what we see here is really high loadings. I mean, imagine paying 10% of your 10 weight percent, of your material is graphene, which is the most expensive thing, right? So then by just doing it random, by doing different processes, you can get the weight down a little bit. The conductivity suffers, but you still get some decent EMI shielding. Now, if you start going into our pre-networks, where we're doing getting the graphene or kind of in its conductive state and in its kind of semi-ordered and grow it in different ways, solution mixing, CVD, freeze casting, right here, we're seeing lower loadings in these, not so much in those, but decent conductivity numbers and really good EMI numbers. Okay, so we're less material, still getting good numbers. Now, let's go to the pre-network stuff. We're starting to get less than 1% here on some of these with alignment. Look at that, less than 1% on 3 of these with alignment. I'm not sure why that was 15% and still had this poor conductivity. It must be the processing. But if you look at this is reduced graphene oxide, PEMS. These are the same thing in epoxies. We're seeing really good numbers here, really low loading, really cost-effective EMI shielding. So, how do they do that last one, the bidirectional freeze casting? So, kind of crazy. I've done a lot of freeze casting myself, and their rule is kind of, their way to do it is kind of weird. You take a copper plate, and then you cast a wedge of silicone. Okay, so the wedge acts as a insulator. And then you put a dry ice or liquid nitrogen on the bottom here. You pour your solution in the top, and so it's freezing from this point in this direction and that direction, up and over at the same time. As it does that, the crystals of the fluid you're using, I believe it's water because this is graphene oxide, it's growing away from the coldest part of the plate, which is this front edge, and it lines down. So there's no insulation there, so it's freezing from that point and going all the way up to the highest point of the wedge, and therefore that aligns everything. So when they do that, then they just take it out and freeze dry it. So they take all the water out, and it stays that puffy area because there's nothing to collapse it. But of course, graphene oxide is not very conductive, so you do a reduction in an oven, and then you do like a vacuum infusion of a curable silicone product. And once you do that, you have order in one direction. Notice the spaces in between the different layers of graphene oxide before putting the silicone in. And then after it, the silicone is supporting them, and you have the different layers right here, and the silicone's in between. Okay, so let's talk about some results for this particular material. Oh, no, we didn't do it. Okay, so, but look at this. Super low loading. Weird freeze drying, but freeze drying is scalable. They do it all the time, and it's really low loading, really good system. It gives us it. And there was a difference in the with the grain and across the grain. I didn't put that slide in. So in this case here, we have a way of getting order before making your composite. Order before your composite might be easier. Now, how else could we get order? Let's say we made it in a random way. How else could we get order? Mechanical. We could do a a stretch, or an elongation, turn it into a fiber. Just imagine you would get all the random particles start to align because of the draw of the dielectric material. You could get the drawn fibers having an order to them with conductivities in these levels. Okay, so now where do we want to be for which use case? Well, this is a pretty little graphic I got. Most of the time we want things to be insulating, and so we want them to be very low, between the 10 ohms per square, excuse me, 10.
That's it's resistivity, right? So you want
Yeah.
high.
Yeah, the resistivity. So you want it very resistant and very high right here. But then again, there are some applications for anti-static at that type. You still want your low conductivity, but you want it to dissipate static. And so that's just a little bit higher. Now, so that's anti-static, so it won't build static. This is if you already have static, like the top of an electronics bench, where you want it to drain immediately when you touch the bench or have your cup put on. And then above that, we want a shielding for EMI shielding or semiconductor systems, or then of course only metals really apply up here really well. So use controls where you want to be. So is 10 to the minus 7 good or bad? I don't know. What are you going to use it for? How much is it going to cost? How much more does it cost than what's already there? Those are the things you're going to look at. So now I want to talk about carbon nanotubes. I'm going to compare carbon nanotubes, graphene, and all these, and a few of the other pillars. In this particular one, we're looking at multi-walled carbon nanotubes and polyamide 12, or what's also called nylon 12. So first of all, the polymer is one of these. The polymer is really good because it is melt processable, it's fairly inexpensive, it's got a nice hydrogen bonding group and a polar group, so that if you have functionalization, it will help disperse. The top one here is nylon 6,6, and the reason it's nylon 6,6 is you have 6 carbons in between those 2 nitrogens. You have 6 carbons on this thing too. There's 4 plus the 2 carbonyl. So the 6 and the 6, that's why it's nylon 6,6. It's made from 2 different monomers. This one's actually made from a lactam, where it ring opens to make the polymer. We call it nylon 6 because those bicarbonate nylon. And then nylon 12 is another lactam. It's just a slightly longer. A little more thermoplastic, a little less hydrogen bonding available to it. Not quite as strong, but not that hard to process. Okay, so for this one, we're going to do that nylon 12 or that PA 12. Okay, so the materials that they're choosing, they're going to compare 4 different materials that they have. The first one is the Bay tubes, and around 15 nanometers in diameter, but pretty long, up to 10 micrometers long. And so we'll see that this has a nice fibril structure here, but this is the blow up of these particles. It kind of comes as an aggregated particle. Now, the next thing they have is this Nanoseal. Nanoseal looks like it is not near as dense as the Baytron was. It's a lot lighter. It's got the fibrils in it are a little bit narrower and a little bit shorter, but they look like they're easier to disperse. They're already kind of puffed, if you will. And then there's the future carbon, which is here. This is the future carbon, which is, I think, their product. And it is fairly short chains of these carbon nanotubes, but they look to be fairly low density. And then the last one is the other Printex, which might just be a toner printer cartridge, but it seems to be particular. It's not long, it just seems to be 30 to 50 nanometers in diameter. Seems to be part of it. So we have two that are long, one that is kind of clusters, one that's round. Now notice the tap density, the bulk density on these right here. The bay tubes are aggregated into those pellets. So they have a fairly decent density right here. The Nanoseal and the future fiber are super puffy. They have a lot of empty volume. So that might make them easier to disperse. And then the Printex is small particles, but they're very dense. Okay, so let's compare and contrast. So let's just first look at the percolation threshold. So they measured by filler content. Notice the max filler content was less than 7 here. We're starting down here. We're getting up into the conductivity range, volume conductivity range, 10 to the minus 4, which is good for a lot of things right here. But the open cells down here are the measurements below the threshold, the percolation threshold. The line here is the imaginary calculated line of where the percolation threshold is. Okay. So the filled ones are actual data. These are actual data. The lines are generated based on those two sets. Okay. So if we look here and kind of draw, a line saying it actually probably comes down like this somewhere here. But we have like a little over 4.5, about 4.5 weight content of these nanomaterials to get to our percolation threshold. And that's for the Printex, the spherical particles. Okay, we kind of predicted that, right? Because the longer aspect ratio, we should hit percolation threshold sooner. So seeing that the spherical particle has the highest loading makes sense. What's next here is the gotta be these, so the bay tubes. Okay, why aren't the bay tubes like gangbusters? Dispersion. Because dispersion, that huge, that packed density, they're packed into little particles. You have to shear those particles apart to get it out. So we have, about 2, and then the other 2 materials are here, like just over 1 and just under 1. You're seeing there, and notice they all get about the same ultimate conductivity right here. So aspect ratio, the 2 longer materials are the ones that hit the aspect ratio first. That's almost half of what the not so long didn't actually give us a length for this, but we know these are spherical around 30. So that's the difference here with the aspect ratio. This is not order. This is just aspect ratio. But what they also did was something cool in the fact that they said, well, obviously the the tubes are not dispersing as well as they should. So they did a study where they changed the process they were using to see if they can enhance it. So what they did was they did one where they did a low viscosity shearing experiment and then cast it with an excess of the acid catalyst, the acid, carboxylic acid. They did it low with the amine in excess, high viscosity, and with acid and amine. So they saw a change there. So in the case of the high viscosity with amine in excess, we see about the same numbers we get. We barely get to this up at the, somewhere between 4.5 and 5. So high viscosity is not helping us. The amine is not helping us. Okay. So then we go to the boxes here, and that's the low viscosity with amine in excess. So that drops it down a little bit. And this is the high viscosity with acid excess. And this is the low viscosity with acid excess. So that means that having a slight excess of the acid in their material, it actually helped disperse the material. And being able to use a low viscosity process helped disperse the material. So they got all the way down to this 2 thing, even though they were way up in here before when they did it the first time, they got it all the way down to 2 by changing their process. They knew that bulk density was too high and it wasn't dispersing. So they found a way around it. So I thought that was very clever. They didn't do this with all of them, they only did it with the Batron because they felt it should have performed better because it should have had a longer acid. All right. Questions on that one? So those are carbon nanofibers. Oh no, multi-walled carbon nanotubes. Sorry.
Does acid excess, that would affect, is that just adding functionalization or?
So the fact that this is, this right here, when you do the polymerization, it's really weird because you put it in as liquids and then you put in your catalyst system and then it stirs and all of a sudden it goes. So I don't know, I haven't figured out why, but it might be whatever was on the surface of the Batron were, pulled into the solution by the polysilicon acid.
So these were all polymerization.
These were in situ polymerization.
The weak acids, right? They're weak acid, right? Weak acids. The acids they have to use.
Yeah, they're carboxylic acids, weak acids. Because when you polymerize these, you also have a salt of one of the monomers, and you have that, and then you add additives. I've done it before, it's really. Bought a kit. Okay, so now I'm going to switch over to nanofibers from the nanotubes. Okay, and this one was, they were looking at the same materials, the same fibers and the same polymer, and they processed it 2 different ways. One was using 2 different kinds of melt mixers. Okay, one's a chaotic and one's a standard. So that's what I want to compare here. So we're comparing apples to apples. It's all processing. Okay, so we have our material. We have a specific value of PMMA. This melt flow index is going to help us be able to calculate shear. And the processing temperature changes, and what we should see, nice low elongation on breaks of good PMMA. And then the material that they got was the pyrograph, and they were just using it to disperse in my system. Notice that this is a diameter, it's in micrometers, but it's 60 to 200 nanometers. So it's kind of in that range barely, but it has that length of 100 micrometers. So that's kind of an interesting thing. So they're not as small as some of the stuff we've been using, but they are used. So the difference in the mixers are that what they do is these are full mixers. They put their material in, they put their polymer in, and then they run it for X number of minutes at X temperature. In the traditional carbonate here, you have blades that'll intermesh, and usually they're kind of tilted, so they'll kind of go past each other. And these are run counter rotating right here. And so you have some shear around the walls. You have some shear when the paddles come near each other. They're counter rotating, so they're literally pushing the material in the same direction at the same time. Okay, so what they're getting is the material comes in the middle, it gets sheared apart, and then sheared apart and sheared apart. But so in the other one, in the chaotic mixer, we actually have the rotors here spinning with the heat, and they're taking the material along the surface using the surface resistance to flow, and they're pulling past it, but they're rolling in the same direction. So this material is going to shear past this material, making it shear past each other and get a different level of order. Again, the paddles in here actually kind of disrupt that order. These actually keep a linear shearing system, keep a zone where it's laminar flow, flowing together.
Are they the same speed, the paddles on that?
I believe, let's see. Yeah, they did a whole study where they did them at speeds, but they targeted the same speed for the same amount of shear.
The two paddles in one thing are at the same
Yeah.
speed, they're not one's going faster.
Correct. Yeah, they're interconnected, so they don't hit each other. So then here's the results from that right here. So the raw bender, it had a nice percolation threshold somewhere around 5 right here. And the transverse to with the direction of flow had about the same conductivity. Okay, so that's making me think, number one, this is a pretty high threshold. And the fact that these are the same is telling me we probably don't have any order. We have a disordered system. Okay, which is counterintuitive because we're using the chaotic to make an ordered system. In the other system, we have started right here at 1, we're getting our percolation threshold and a higher conductivity. But now look, we have a different transverse conductivity. So that's telling me we're having order in the direction of flow, allowing us to have more pathways in the direction of flow, fewer going off in the other directions. Okay, so gosh, you've got to take a couple SEMs of this. So this is what they saw. This is optical microscopy. They saw in the chaotic, they had laminar shear zones. And the nanomaterial was collecting in the laminar shear zone. So they were all ordered in that direction. There's almost no order in the bar bender. We don't see anything. We see little individual particles dispersed. There's no order here. Most of the material is in that direction as well. So that's why they saw such a much better, much lower percolation threshold, much higher conductivity, and bigger difference in the transverse electrical properties. Okay. Okay. So could we do this industrially? Yeah, because most industrial lines tend to be continuous and linear. You get your shear flow to go continuous and linear, you can actually produce this on a pretty good scale. Because you're trying, all you have to do is design your system to have the shear in the correct direction. Then, if let's say you made it as a fairly thick sheet, then you draw it out, get even higher. So, okay, sorry.
But the dispersion in the second one, that chaotic one, would be greater, right? The dispersion that had the plates due to the higher shear.
What was it better? I think that it was actually not as good, but it was ordered. So I think the particles had more. They got. They were. What's the word? They were forced into certain zones, and so there's more polymer in other zones and more nanomaterial in these zones, but they're all ordered in a specific direction.
So is it important that they should be dispersed and should be in the line of the current or something?
Yeah.
For conductivity, you want the lowest resistance between, okay, think of the percolation threshold as your serial resistance, okay? So, you know, the resistance to go from here to here, right? So you have your nanoparticle, you have a resistance between the two nanoparticles and the resistance. So what you want is the lowest serial resistance for that system. So you can have well-dispersed polymers that are correctly spaced, so the hopping distance lowers your surface, your series resistance, or you can have more like almost like wires or sheets of conductive material conduct. Even though they're not well dispersed, they'll still be able to conduct. So you can have it either way. In general, the better dispersed your system is, the better conductivity you have, because you have more of the conductive pathways possible.
Because in the second one, if you will see, they have the similar kind of like arrangement in that opposite direction than the conduction. but I think might be they have the holes that stop the conduction, the lower one, third one, right?
Yeah, so these are the ones that were done in the other one, the counter.
Plates, yeah.
So let's see, this looks dispersed, well dispersed, but maybe these aren't close enough together in the lower loadings to get them to the percolation. There, it looks like the particles are aggregating in sheets, almost like ribbons. And that's giving them the higher tone. Okay, so now we're going to go to graphite. So, and we're going to go to expanded graphite. So instead of going to the graphene oxide and reduced graphene oxide and all that stuff like that, we're going to go to the cheaper version, which is graphite, expanded graphite. So in the case of an expanded graphite, they just take natural platy graphite and they infuse a liquid into it, sometimes a gas, but it's under pressure, and so it's a liquid that goes in, and then through rapid heating or rapid loss of pressure, it can blow some of the things apart. Okay, now they're not going to be individual sheets. You're going to see them kind of puff up. And anybody know what vermiculite is? Vermiculite is, it's a plating aluminum silicate that they use for packing and like boxes and stuff. It's a gold stuff that gets all over everything. That's a natural mica, and they do this exact same thing with steam. They expand it, they puff it up, but it doesn't blow apart into individual plates. It stays as this puffed structure. Okay, not unlike popcorn. So when we look at the grainy part of the particles here, we can see that the edges of the particles here on the regular stuff, this is what they look like here. So this is hundreds of plates of graphene in each one of these little platelets. That's full graphite. Okay, and then when you interpolate them, it expands a little bit right here. But once you take that and expose it to rapid heating, you get these structures here. It can't completely blow apart. It's not volatile enough, but there's enough energy between the plates to keep some of the little pieces together. But there's no force making them go back together. So they stay expanded. So this is what we can call expanded graphene. So it still has some of the features of graphene, but it's not individual plates we have to worry about. Expanded graphite, sorry. So each of these might not even be individual graphene sheets. They might be 2 or 3, but it's definitely, much higher surface area than the unexpanded graphite. Okay. Oh no, running out of time. Okay, so let's look at what they got here. So they did a couple things where they looked at the graphite by itself, the platy graphite without any, they process this the same way, and the expanded graphite, and this is weight percent here. So they see what we expect to see. The more cylindrical ones have this longer tail and a higher percolation threshold, around 3. We got a percolation threshold just under 1 here. But look how even the conductivity is. There's no slope in that conductivity. Here we have some platelets maybe separated, but mostly chunks. And then it's starting to get up to here before you get to the, not quite the same conductivity, but pretty close. So it's actually kind of nice that, they have, number one, they use so much less of the material that they do have to process it to get it to that. Okay. And
I think we should use the expanded one because there is no difference between the conductivity that much.
Well, it depends on your cost, right? If you want to do a loading of 6% versus 1% to get the same conductivity, is there a cost benefit there? And plus, what's your use? So yeah, I mean, I think that if this process is not too expensive to make the expanded graphene, if they just infuse it with like a hydrocarbon and then hit it with steam, which is what they do for, well, with mica, it's water and steam. So if it's an environment, if it's a scalable process, yeah, expanded graphene is definitely better. And it's probably cheaper than a lot of the other, because you're starting with natural graphene. You don't have to make it by seed. Okay, that's what I have for today, and come back on Thursday for part 2. We're going to look at some other fillers and some other analyses, and I'm going to kind of sum up some of the general trends we're seeing with the electrical conductivity. All right, I'm going to